Hello, my name is Greg Perugini, and once again, welcome back to Physics for the 21st Century. Today's topic is Kepler's laws. Now, we covered a little bit of this when we talked about gravitation in a previous topic, but we're going to cover all three of the laws now. And the first law is what we can call the law of ellipses. And as Kepler saw back in the 1600s, that the sun is not at the center of an orbit. And this is greatly exaggerated in our orbits around the sun for our planets. But it is at one focal point, the other focal point being empty. So if I drew or had a string, let's say these were two pins, and I had a string here, and then I had my pen and I just drew it around, it would give me my ellipse. So that's the first law. Incredible insight to come up with this using the data from Tycho Brahe. And so that is fairly simple, but a very powerful statement. The second law is the law of equal areas. And that if I have a ellipse, he noticed that the farther away we were, he didn't have a true definition of gravity. That came later with Newton. That the amount of time it took to get from point A to point B, if that's like 8 days, it would go faster, cover that in that same amount of time, 8 days, a larger area, or I should say a larger path. But the area here and here would be equal. It would sweep out the same area for a given period of time. That's the second law. Very powerful, and based on gravity, the farther away we are, we move slower. Those planets that are farther away, they of course have longer years. Those planets that are closer, like Mercury, have shorter years. The third law we often call the law of harmonies. Now, we saw this defined another way in gravitation. Gravitation was something unknown in Kepler's time. This is sort of added in, this part here in the brackets is added in the time of Newton. He just knew there was a relationship, a squared relationship of the period, the amount of time to go around once around the sun, has a relationship, a proportional relationship to the radius, how far away it is, cubed. So if we're doing this for our sun, well, we know what the mass of the sun is. He didn't at the time, but we know it now. That is 1.99 times 10 to the 30 kilograms. A very large portion of our solar system is the sun. And of course, with Newton, we have the gravitational constant. He didn't know what that was either at his time. It took Cavendish later on to come up with this number, 6.67 times 10 to the negative 11. But now that we know that, we can come up with K, which is everything in that bracket. If we take 4 pi squared and divide it by these two numbers multiplied together, for our solar system, we're going to get a number. Okay? Now, what is that number? Well, you can check my math. 2.976 times 10 to the negative 19. That we're going to call K for Kepler. And so you see that here. So as I said, in Newton's time we could add that on with the insight of gravity and the mass of the sun. Maybe it's best to do an example. Let's do one now. How long is Mars's year? In other words, how long does it take to go around the sun? We'll do that in Earth days. So we know this relationship. We know what K is, right? We just got that. For our solar system, it's a constant. For other solar systems, of course, it's not going to be a constant. Or it'll be a constant for that solar system, I should say. But the mass of the sun, remember in the brackets, 4 pi squared over GMS. If it's for another star, if it's another star, you got a different mass. But anyway, if we're doing this for our star, we already know that K value. And we know how far away it is. We can look that up. Perhaps it's given to you. Let's say it's 2.28 times 10 to the negative 10 to the 11, I should say, 11 meters away. That's one way to measure it. Now, we could also measure it in astronomical units. We'll talk about that in a little bit. But if I know that, and I cube that, multiply it by this number, then whatever I have there, take the root of, I will get what T is equal to. What is T? So you could do that calculation yourself, and you're going to get something like 5.94 times 10 to the 7 seconds. And if I divide that by 24 hours and 3,600 hours, 3,600 seconds to an hour, that would give me how many days? About 687 days. Okay. Not quite, but almost two of Earth's years. Now, you may also have to work through that we're going to be dealing with astronomical units. It's a little bit arrogant, but it is a measurement of time, of space. An astronomical unit is the distance from the sun to the earth. That radius is 1.496 times 10 to the 11 meters. Sometimes you'll be getting a measurement like a planet is 4 astronomical units away, 30 astronomical units away, from the sun or from a particular star. Sometimes we can measure stars in terms of sols. It's 2.3 sols. In other words, its mass is 2.3 times our sun's mass. So just be aware of those conversions for the test. And in that assessment, just make sure you know how to work through Kepler's equations using K, and also for any star, the mass would be different. So be aware of Kepler's equations with gravitation, as well as using that K value would help you speed you through the equation quicker. The answer in question may involve a certain amount of sols or 13 astronomical units or a certain amount of astronomical units. And these problems are not multiple choice. They're fill in the blank. So make sure you get your work correctly written down, and watch your units. Make sure you specify your units. If we're talking in seconds or periods of days, or if we're talking about in terms of meters. So that's Kepler's law in more detail than we did before in the gravitational section. Good luck.